Okay, so we are very delighted to have Dor Minzer as our next speaker. Dor did his PhD at Tel Aviv University and a postdoc at the IAS, and he's now a faculty member at MIT. He's also an organizer of this amazing event and has helped put together some of the talks in the program. Dor is an expert in complexity theory broadly. You've already got a glimpse of some of the amazing work he's been doing, and he'll tell us more about his work on PCPs.
Okay. Thank you, Shubhangi, and thank you all for coming. So first of all, congrats, Mark. I'm not going to talk about any work that I've done with Mark, but I'm going to talk about something that Mark really likes, which is parallel repetition. It's not in the title, but it will come along as we go through the slides. So this is joint work with Mitali Bafna, Nikhil Vyas, Noam Lifshitz, and Ziwei Yan. So let's start with the basics. So introduce PCPs. So I hope that you know what 3-sat is, because Subash defined it. So you're given a 3-cylinder formula. Question, is it decidable? So that's a question we really like. We even teach about it in complexity courses. And we do that because it captures the class NP, which we really care about. We've known this since the 70s. And oftentimes when we talk about it, we take the view of verification. It's very easy to verify a solution to 3-sat. If I give you an assignment, it's very easy to tell whether it is actually a solution or not, because you just go over the clauses one by one, you check that they are all satisfied, done. But what this talk is going to be about is about more efficient verification, which is what PCP is about. So to make a step towards it, I'm going to first of all take a bit of a weird view of the same verifier, which is a randomized view. So how can I have a more efficient verifier using randomness? Well, I'm still given a witness, W, which is presumably a satisfying assignment to fire. So instead of checking all of the clauses, I'm just going to check one clause chosen at random, read 3 values, done. It's a very efficient verifier. It only reads 3 bits from the proof. So what can we say about its performance? Well, if I indeed give you a correct witness, you always accept. That's clear. But if W is not a correct witness, if it does not satisfy fire, well, there exists at least one clause where you fail to satisfy. So the probability verifier accept is at most 1 minus 1 over the number of clauses, which is less than 1, but not much less than 1. So while this verifier is very efficient, its performance is not that good. The soundness that it has is not very good. You are not going to bank your life on this gap. So how do you improve this soundness? So that's a difficult thing to do, but this was already done in the 90s. This is a result known as the PCP theorem. It asserts that there exists a different probabilistic verifier, which I'm going to denote by PCP, that when you give to it fire, the formula, and some other witness, it's not an assignment, it's some bizarre thing, the verifier does the following thing. It only reads 2 locations from the witness, and it has the following guarantee. If I is satisfiable, then there exists a witness W that makes the randomized verifier accept with probability 1. Now, on the other hand, the soundness, if I is unsatisfiable, then no matter what witness W I give you, the probability that VPCP accepts is at most 0.99. So this is like a much better result compared to the previous one, because you have some constant gap between the completeness and the soundness. Okay. So now I want to make a few points. So first of all, the length of this witness, now it's polynomial in N. It's a bit longer than the length of an assignment, let's say n to the 10. But when we talk about complexity, usually polynomial is nothing, we allow it. Secondly, I write here that the witness is from some abstract alphabet sigma. You cannot get Boolean alphabet because I sort of insisted on 2 queries. So it can be like size 3 if you want, but this is really a minor point, so you can kind of ignore it. So it's great, right? You get pretty much the same size witness, pretty much the same alphabet, but much bigger gap. And indeed, this is a very powerful result, and it has many, many applications throughout TCS, very influential in hardness of approximation. But in life, whenever you have something, you can hope for something better. So this is what happened after this was proved. So what can you hope to improve further in this theorem? So you can complain about many things in this theorem, and people have been complaining for 20 years or more. But today I'm going to only raise 2 of these complaints. So one complaint is, well, it's true that we get a constant gap between the completeness and the soundness, but can we get even a larger gap? So 0.99 is pretty weak. Can we get something better? That's complaint number 1. Complaint number 2 is, well, polynomial length is fine, but ideally we would like a linear length witness. Like we don't want to blow up the witness so much. So we get a better length PCP. And I'm not going to bother you with the application of this. You'll have to trust me that these 2 parameters actually arise in applications in this bunch of areas. So they are well motivated to study. And indeed, oftentimes when you manage to improve one of them, it directly implies improvements to several results in the literature. We'll see an example later on. Okay. So let me tell you what is known about these 2 problems. So for the soundness case, well, Ran Raz, in the same work that Subhash mentioned, managed to show that if you have the PCP theorem, then in a black box way, you can actually prove a different PCP theorem, but now the soundness is epsilon, where epsilon is as small as you want. This is by the well-known parallel repetition theorem, which we're going to see later on. And subsequently, there have been many, many works about it. And it's well studied. One limitation of parallel repetition that we'll see is, while you can get arbitrarily small soundness, you cannot make it sub-constant. So you cannot make it to be vanishing with the instance size n. So that's something that is also been studied, starting with the work of Ral Safra and a bunch of other works. But the catch in these works is, while they get sub-constant error, they don't manage to retain this property of having 2 queries. They require more than 2 queries, which is annoying for most applications. If you want a truly sub-constant soundness and 2 queries, then this is a significantly harder result due to Moshkovitz and Raz, and this was later abstracted by Dinur and Harsha. Cool. By the way, if there are any questions, then please feel free to interrupt. Now about the length. Well, shortly after the PCP theorem was proved, Polisuk and Spielman managed to show that you can get a near linear length PCP, namely one of size n to the 1 plus a little bit, but the soundness of it is kind of close to 1. In an incomparable result, Benson and Sudan showed that if you're willing to compromise on the soundness a little bit, and have it still far from 1, but only 1 over log n far from 1, then you can go from near linear to almost to even nearer linear. I'm going to refer to this as quasi-linear. Yeah. Sorry,
these for constant alphabet size?
Yeah, so these are for constant alphabet size. These are not. Yeah. So whenever you talk about sub-constant soundness, you have to allow that. Yeah. Cool. And lastly, Dinur, in a reproof of the PCP theorem, showed how to sort of combine this soundness and this size. So she managed to get the best of them. She got quasi-linear size and soundness, which is bounded away from 1 by a constant. And that was a quite significant use of expander graphs and so on and so forth. But if you notice here, so this soundness is bounded away from 1, but it's not like epsilon soundness, like parallel repetition gives you. And sorry, one more result, sorry. So actually the same paper, Moshkovitz and Raz, so actually if you stare at it, they also managed to get quite a good size, a bit larger than Dinur, but they managed to get epsilon soundness, or epsilon is as small as you want. So the question that we are going to talk about is whether you can push the soundness of 0.99 further while still having quasi-linear budget. And to see that, we are going to first of all discuss parallel repetition and see what it gives you.
Do you care if it's polylog or to the root log? Or so is this also quasi-linear or just the polylog?
No, so for me, quasi-linear is this.
Is it easy if you're willing to do anything that's less than anything normal, or it's still hard?
What do you mean easy?
Does it follow by combining existing results?
So this, if you allow a little bit more log, then this is the, I mean, Moshkovitz and Raz already get it.
Epsilon is like 1 over polyen, or?
No, epsilon is 1 over polylog. Yeah, no, polyen is not. No. More questions? Okay. So if not, let me tell you what is parallel repetition, or kind of remind you what it is. So here is the task that parallel repetition is trying to solve. We have the PCP theorem. It's a nice theorem, but it only has soundness 0.99. How can we use it in a black box to get a better PCP theorem? Well, the most naive thing that anybody that sees this says, okay, let's just run the verifier several times and accept if it accepted in all of the runs. So that's true, that works. It's very easy to prove it. But then the number of queries the verifier makes actually goes up. So each time you run it, it does 2 queries. If you run it k times, it does 2k queries. Not good. So why is it not good? I'm not going to get into that. I will just tell you that for many applications, certainly in hardness of approximation, getting 2 queries is crucial. If you get 3 queries, you have no starting point, but 2 is very good. So this motivates the question of how can you do amplification while keeping the number of queries to be 2? Yeah, so in this business, the above thing is called sequential repetition because you repeat it one after the other. And the solution to keep the number of queries to be 2 is what is called parallel repetition. So you do the same, morally speaking, but you do all of these runs in parallel. Yeah, we'll get that. So one way to think about it is, as Subhash discussed, because I'm viewing it from a verification point of view, I'll take a different but equivalent view. So you can think of the witness of the VPCP as some string, W1 to WM. So the k-fold repeated verifier will have a much longer string, W prime. So the length of this new string is roughly m to the k. So here you have an entry for each k tuple of indices, I1 to ik in this proof. And presumably, this symbol is going to be the concatenation of the k symbols corresponding to it in the first proof. Okay, so that is what parallel repetition amounts to. So let's see what it gives us. So it's very easy to see that, in the yes case, in the completeness remains 1. But it's much harder, and this is the parallel repetition theorem, to show that if the original verifier VPCP accepts with probability at most 0.99, then this k-fold repeated verifier accepts with probability exponentially small in k. Kind of the issue here is that while we really want this W prime to be, as we said, take W and tezorite is k times, W prime could be anything. So you have to deal with that.
Question. You say after the k is going to be like with repetition, like is it M to the k or M choose k? Does that make sense?
M choose k.
Okay, so
Yeah.
it involves you could have repeated
So k is going to be much smaller than related to m. So the difference is not going to be that big. Yeah. But you should think about it as M choose k if you want.
Okay.
Yeah. Okay. So there are several issues with parallel repetition. So as Omri already said, it leads to blow up in the alphabet size. So that's a topic for a different talk, not today. For today, we're going to complain about the fact that it increases the length of the witness by a lot. So our original witness was of length m, and now the new witness, it's of length m to the k. So if k is constant, it's still going to be polynomial, but this approach can never give you something near linear. It can never give you quasi-linear or anything like that. So the main question that we address in this work, so the main question that I'm leading up to, is can we do amplification with less blow up in the length? So of course the holy grail will be linear blow up, but that's pretty hard. Okay, so now with that in mind, let me tell you our main result. So the main result is that actually you can do it. You can do the simplification procedure more efficiently. We'll see later on what I mean. And if you do that, then you can show that there exists a PCP construction with quasi-linear size and arbitrarily small constant soundness, epsilon. Yeah, so that sort of gets a version of Dinur's theorem, but with arbitrarily small soundness. So the proof uses a bunch of things. I'm aware, I know some of them well. So it uses these sort of things, which is quite fun. So I'm not going to tell you all of them. I'm going to tell you a bit about some of them. But before I do that, and because this is a TCS talk, I first should tell you applications of this and what is this good for. No, it's a white box.
If I wanted epsilon to keep dropping, what's the dependence? It's going to be 1 over polynomial epsilon?
I actually don't know.
But
so the bound.
What's the best that we can get with this?
So the bound that we get is like n times log to the n, O of epsilon of 1. And I actually don't know to tell you what is O of epsilon. I think on an optimistic day, it's probably doubly exponential in 1 over epsilon. But the way that the current paper is written, it's some tower.
So if I wanted epsilon to be 1 over n, my best bet is still
1 over n? No, 1 over n you cannot get. No, because then n is going to be larger than n.
no 1 over all them.
Ah, yeah. So maybe this can give you soundness, which is like 1 over pi log log. But we did not check
But
it.
if you wanted for things like insecurity, where they actually want it to be very, very small.
Oh, yeah, no. Yeah, that's not the way. Mhm. Mhm.
But for epsilon, that tends to 0, or that one?
Yeah, epsilon is equal to 1 over pi log. Yeah. Yeah. Again, in principle, this should give you some subconstant error, but I mean, you have to do some nasty computations about things that I don't know too much about. And sort of it's it's somewhere in there. Yeah.
Did you already say this is constant alphabet size or no?
Yeah, this is constant alphabet size. The alphabet size is actually exponentially 1 over epsilon. Yeah.
Does it need for epsilon to be subconstant? It necessarily needs to be superconstant.
The alphabet. Yeah. In fact, all of the PCPs that we know with soundness epsilon that have 2 queries have exponential in 1 over epsilon alphabet. That's, I mean, presumably you could hope for polynomial, but that we don't know. This is 2 queries, yeah. Okay, so let me tell you some applications. So one class of applications is hardness for things, assuming, let's say, ETH. So assuming ETH, you can prove the following result. For every epsilon, if I allow you a little bit less than exponential time, not only is it hard to tell whether a given formula is satisfiable or not, in fact, it's even hard to tell whether it's fully satisfiable or at most 7 over 8 plus a little bit satisfiable. So if it's hard to decide result, it's hard to approximate it with only very small loss in time.
And do you really need the polynomial for it, or does it just affect the time?
So you mean our result, how it helps here?
I'm saying, would you get something similar to this statement with the previous result?
Yeah, so yeah, but the time bound would be worse.
Replace the polynomial with what they have.
Exactly what you expect. Yeah, it's the inverse of the. And you can prove similar results for a bunch of other problems, which I'm not going to mention. Another application, well, not of the theorem, but of the technique, is something actually from distributed computing. So I'll just say the statement, even though it's not going to make sense now. It will make sense in the future. So we prove that there exists an n-vertex graph with polylogarithmic degrees that admits good routing protocols. And what good and what all of this is, I'm going to define shortly. I just want to sort of plant in your head that there is some distributed relation. Okay. Cool. So we'll see this routing stuff very soon. So I do want to give you some idea of what's going on in the proof. And for that, I'm going to tell you more about 2 components. The first of which is the direct product testing problem, which is a problem from probability testing, which is very important in this context. So if you lost me talking about PCPs and all of that, that's a good time to come back in. It's you can think about this problem by itself if you want. So this is a problem that Goldreich and Safra came up with. And the motivation was to simplify the proof of the PCP theorem, but we don't care about that. So you can think of the problem as follows. You have a function f from 1 to n to sigma. If you want some association, you can think of f as specifying an assignment to some 3c in a formula. That's a good analogy. And given f, you want to consider the direct product encoding of f, which is the function capital F, which take k tuple of indices and attaches to each one of them a symbol from sigma to the k in the obvious way. You just apply little f on each one of the elements of the set and concatenate it. So that's the direct product encoding. The direct product testing question now is the following. I give you some function, g from n choose k to sigma to the k, and I want you to test locally whether this g is a direct product encoding of some function or not. So the word locally here is really important, right? I can just look at the entire G and come up with a candidate if I can do whatever I want. So the word locally means I only allow you to look at 2 locations in G. That's it. And based on that, you have to make a decision. Okay, and this problem has been studied quite extensively, starting with the work of Goldach and Safra. And pretty much if you think about this problem for maybe 5 minutes, you'll come up with the most natural test, which is what people have been studying. So what you do is you pick 2 inputs to capital G, A and A prime. In a little bit of correlated way, you say that the intersected size, let's say root k. Don't attach too much value to this root k. Anything between 0 and k, which is not too close to other endpoints, is good enough. So you sample an A prime, you read G at these 2 locations, and then you notice that if G is indeed coming from some little f, then of course the elements in A intersection A prime should get the same value in GA and GA prime. So you check whether that's the case. Done, that's the test. So what can you say about the test? So of course, if G is a valid direct product encoding of a function, it passes with probability 1. Like, that's trivial. The interesting question is what happens on the other direction. Let's say that I have a G, and I tell you that it passes with probability non-trivial. Let's say at least delta. What can you say about G? So here is an example theorem due to Dinur and Goldenberg. There is a slight lie here, but doesn't matter. So they show that in that case, there is a valid little f such that G agrees with little f on polydelta many of the sets A1 to AK. So in words, if G passes this local test with noticeable probability, then at least on some chunk of its domain, it acts as we expected. And in some sense, this is the best you can hope for. So that's the correct answer. So that's a theorem that is known as a direct product theorem. And these are powerful results. You can directly use such a result to get a hardness amplification result. This was done by. So if you want to fix delta, k has to be sufficiently large compared to delta. The k has to be at least, let's say, 1 over delta to the 10. Okay.
With modern thinking, is there a way already to understand the Moore's theorem with just per repetition with a very small starting soundness, or
we'll get to it.
Still too many steps in between?
No, we'll get to it. I can tell you exactly how you should kind of think about it. Okay, so you can use it for hardness simplification. But there is one drawback, which is if you look at the size of capital F, by which I mean that's the size of the truth table, it's much larger than the size of little f. It's the size of little f to the k. So this is the same blowup as we incurred in parallel repetition. So while you can use this as an alternative to parallel repetition, it has the same drawback. So now we come to a natural question. Can you find sparser direct polar testers? Can you come up with something that has a better size blowup? Maybe not to the k, maybe something else. So this question was asked by Dinur and Kaufman, and they managed to show results stating that if you take high dimensional expanders, then they naturally give you, I'll quickly say shortly, what does it mean? So they naturally give you sparse direct product testers, but they only manage to prove it for the case that delta is close to 1. This is the 1 minus epsilon case that also Subash was talking about somewhere. So that's good, but you cannot use it to drive the soundness down to, yeah.
Do you mean it is not in principle possible to drive the soundness down to epsilon using HDX, or do you mean using the HDX that were known
This,
in 2017, you couldn't get better than
using this theorem, you cannot drive the soundness down to epsilon. So now comes a delicate point, which is they conjectured that HDX should give you direct product testers, but not that they didn't conjecture that any old HDX gives you that. They said that there exist some HDX that do. That's an important distinction. So why do I mean by naturally give direct product testers? So you know, all of these HDX and sparse direct product testers in this language really amount to a clever choice of a subset, fanciest, of k sets, which is sparse, which has size O of n. Once I specify to you this collection fanciest, you immediately have a direct product encoding, which is just take the previous one, restrict it only to k tuples in S, and you naturally get a similar test as before. A random collection would not, I mean, yeah, there would be not two sets that intersect on that size.
But the random thing does not have two testers.
Yeah, yeah. Okay, I don't know if it doesn't have good testers, but this tester doesn't work. Yeah, I mean, just to get that the first item does not, I mean, makes any sense, you need to specify fanciest with some structure. So, yeah. So this conjecture is true. It was proved independently by Bafna, myself, and Lifshitz, and by Dixon, Dinur, and Lubotsky, building on many works in high-dimensional expanders literature. And what we showed is that indeed for any delta, you can construct some HDX that does give you a sparse direct product tester. And actually, we also showed that it's not true for any HDX. Like there are some HDX where it fails for delta below like half or something like that. So it's not that it's the proof is failing, is actually the statement is incorrect. So there are HDXs that don't work. And actually, if you look at it from the right view, it's the same reason that Dinur didn't manage to go below half in our proof. But that's a topic for a different day. Okay, so I didn't tell you what these HDX are. I will tell you a little bit about it later. So any questions about direct product testing? Okay. So the next thing I want to tell you about is the distributed computing connection. And again, this is a standalone problem that people have studied for different reasons. It goes as follows. You have a graph G. Here it is. You have a collection of pairs of vertices, SITI, which I think of as source and target. You should think of the number of pairs as linear in the number of vertices. And each SI has a message that it really wants to send to TI. But the problem is that TI is not a neighbor of SI. And we only allow vertices to send messages to their neighbors. So how can you do that? So here's the definition. We said that G has an R round protocol if there is a protocol that takes R rounds. In each round, the vertex sends a message to all of its neighbors. And in the end of the R rounds, all of the targets get the messages from the sources. Yeah, that's a definition. So the goal in this problem is to design graphs G that have good routing protocols. So of course I can take the click graph, and I have a very good protocol on that. So usually you want a graph to have small degrees as possible, and you also want small congestion. So you don't want like the star graph where everybody is connected to one and you just route through that. So you don't want any vertex to do too much of the work. So a result by Along, Chang, and Graham, and later refined by Nenadov, says that if G is an expander graph, then you can do it with O of log n many rounds. And O of log n is the best you can do, because that's the diameter of an expander. Yeah.
Small congestion here means something like the number of bits communicated on any edge is order log n times the message size.
So the total number of bits that each vertex sends is, let's say, at most polylog. Something like that. So this is a nice result, but for us, we care about a related but different problem where there are some corruptions happening during the protocol. Same setting, but now we talk about corruptions. So this model of corruptions is the one that was studied by the distributed people, and it goes as follows. So you set up your protocol, but now there is some adversary coming. They can choose to have some small fraction, epsilon fraction of the vertices, and completely corrupt them. By that, I mean control what these vertices send on each one of the rounds in the protocol. Okay. And your goal now is to design the graph G in a way which is resilient against these corruptions. So of course, the adversary can just corrupt the target and say, oh, I didn't get it. So what you want is that the most of the transfers will be successful. So this problem is being considered in the mid-80s, and people have worked on it from then. And the best result that was known is a construction of a graph G that has polylogarithmic degree and polylogarithmic work complexity, which is the measure of congestion. Again, this is the number of bits that a vertex sends throughout the protocol.
Do they use coding in those protocols, or is it a multi-commodity flow model, or do they actually code things?
It's kind of coding things.
Would the answers change if it was multi-commodity flow, if bits were boxes of oranges?
I have no idea.
There is a set of network coding open problems that ask whether it changes answers in various settings.
Okay, I have no idea about it. That's an interesting question.
Also, why do you
about protocol cadences, not just about, like the previous result was just a result about the composition expanding the
Mhm.
So that was kind of a routing.
Mhm.
Whereas here it seems like it's not like just a
Yeah. So you need to do something else. You cannot just stay with vertex disjoint paths. You need to do something else. And that's why I didn't define it in that way. I said a protocol, not yeah. Cool. So that's a fine model, but it turns out that it's not good enough for us. We need a different model, kind of a stronger corruption model, where instead of corrupting vertices, you are allowed to corrupt edges. So what do I mean by that? Same story, except that now the adversary can choose the epsilon fraction of the edges and control whatever is sent there throughout the protocol. So I claim that this model is stronger than the vertex corruption model, because if I want to mimic corrupting a vertex, I can just say, oh, I corrupt all of the edges that touch it, done. But it's more versatile, right? The adversary can say, oh, I corrupt this edge and that edge, but these two I leave alive to save on my budget and stuff like that. So results don't transfer from vertex corruptions to edge corruptions. I mean, they do, except that you need to pay in the degree. So if the degree is constant, it's fine. But if the degree is not constant, then it's actually a big payment. So this model has been considered, but much less so by the distributed people. I'm not sure why. But anyway, as part of our work, we managed to show that there exists a graph G that admits the same performance, except that it's against this stronger notion of corruptions. It is resilient against edge corruptions. Yeah.
Is it possible this is achievable with constant degree, or are there no events?
No, so it is possible, and we did that in a subsequent work. So it turns out that you can, I think that this is, I'm a PCP person, so that's why it is. I think this is the more correct model. And once you look at that, you can actually compose these things. You can compose routing networks the same way you compose PCPs. That composition is not available if you look at vertex corruptions. So they couldn't do that, but once you have that, you can compose it once to get polylog-log degree, and again to get polylog-log degree. And then after you have enough logs, you can apply something trivial. So yeah, good question. Cool. Yeah, so what are these HDXs that I keep on mentioning? I have 5 minutes. Oh, okay. So maybe a bit more. So it's going to be a crash course on HDX, or more precisely a crash slide. So what is an expander? That's going to be my running definition. An expander is a graph that looks like the complete graph. So you've seen expanders, you know what I mean by that. So what is a high-dimensional expander? Well, it is a hypergraph. Namely, it consists of a set of vertices, set of edges, up to sets of size of hyper edges of size D, that additionally satisfies downward closure. Whenever you have an edge of size J, all of its subsets are also edges in your complex. So that's the definition of a simplicial complex. And my running definition of a high-dimensional expander, but now I should stress that this is my definition of spectral expander, is one that looks like the complete complex, meaning looks like X, where I took all of the edges of every possible size. Let me remark here that the reason I'm saying the word spectral here is because when you talk about complexes of dimension larger than 2, there are several non-equivalent notions of expansion. There exists the notion, a topological notion, which is called quasi-Solik expansion and co-boundary expansion, which are actually very important for us. I wish I had more time to talk about it, but I don't. All I'm going to tell you is that they are non-equivalent and they are important. For example, they naturally arise in the context of direct product testing. So let me just give you a feel for what is spectral expansion. So the set XD, you often refer to it as a set of size D clicks. And here is what you should have in mind when I say the word HDX. So while X is sparse, I mean, the size of XD is O of N, it still satisfies some nice mixing properties. For example, consider the following walk. You start with some D click D1, and then you move to some random D click D2 that intersects it at D over 2 vertices. Again, all within XD. And you repeat that. You do it again and again and again. So this is a random walk on XD. My running definition of spectral expander is an X where this walk quickly converges to something uniform from XD. And quickly is, as usual, O of log n length. Yeah, that's kind of the running definition for now. So with this running definition, I can tell you what is the relation to routing, at least in a high level. There is one slight change that I'm making to the problem. So initially in the routing problem, vertices hold the messages. Let's say now that clicks hold the messages. By that I mean that the click D1, each vertex in it has the same message M. It's not a big jump to go to that, but let's just take it for granted. Now we need to route. So the idea, so I have the collection of D clicks and D clicks, and I want to send messages from the left ones to the right ones. So the idea is to use what is called the click-to-click routing protocol, which I'm going to describe to you now, which is, when you see it, it's very, very natural. So first of all, you set up these vertex disjoint paths or click disjoint paths from pairs of vertices. So let's say that U wants to send a message to pi U. So first of all, you find a path in this click path, a click graph that goes from the click of U to the click of pi U. The length of this path is O of log n. And then what you do is you simply propagate the message throughout this path in the most obvious way you can think of. In each round, or in round T, the click dt is supposedly going to have the message. So what's going to do, maybe let me show you a picture. What it's going to do is each vertex in dt is going to send their message to vertices in the intersection between dt and dt plus 1. Now each vertex here, let's say v, got the opinions of all of this click about what the message is. They're going to take majority over these opinions, and this is going to be their value. And next, they're going to propagate it to the next click. Each vector here sends their message to this click, and these guys again take majority, and this continues. Okay. I forgot animations. Okay. So that's the protocol. And I'm not going to bore you with the analysis, but roughly speaking, what's happening is you have what is called the Chernoff bound for high-dimensional expanders, which means that, except with exponentially small probability in D, or more precisely, in root D, the majority is the correct thing it's supposed to be. And because you want to union bound over length L, you need to set up the parameters correctly. And once you do that, D needs to be double log, and that gives you a result. So that's the routing connection. And if you directly use this protocol, what you will get is a PCP of this size. So n times 2 to the polylog log n, which is more than quasi-linear. If you want to get the quasi-linear thing, you need to graduate from clicks. You need to use some bit looser structure, which is called link. It's really the same intuition, but it's a lot messier. Roughly speaking, these are sets of vertices in the complex which are much larger than clicks, but they are still very dense. There are still many edges inside. So that turns out to be good enough for routing. And once you do that, you can go all the way to quasi-linear. So let me conclude now. So I told you about the quasi-linear PCP construction with small sourness, and I told you a little bit about the relation between that and direct product testing and some problems in distributed computing. So the most obvious open problem is, can you get linear size PCPs? That's very hard. We don't know how to do that. More manageable open problems is find other applications of HDX in PCPs. I'm sort of a believer that once there is one application which is compelling, there should be more. And indeed, in a follow-up work with Buff and Kartik CS, we managed to show some application within this fixed parameter complexity business. And as was already asked, you can get a routing network with constant degree, and this is a follow-up work with Bafna. And yeah, I expect there will be more applications of this type of things. HDX seems very useful in the distributed setting because distributed is all about passing messages along things, but not doing it trivially. At least in hindsight, it seems like HDX is the perfect thing for it. So it will be interesting to see if one can find more applications there also. So with that, I'll end. Thanks.